This is Unit 6, Lesson 1, Stratigraphy. For this lesson, our learning target is I can interpret stratigraphic sequences by applying the 4 principles of relative dating. Our success criteria: students can put rock layers in order from oldest to youngest by applying the 4 principles of relative dating, and students can list the 4 principles of relative dating. So when we talk about stratigraphy, it's a branch of geology that studies the order and relative position of strata and their relationship to the geologic timescale. Relative dating is the process of determining if one rock or geologic event is older or younger than another without knowing their specific ages. For example, how many years ago the object was formed. So what this is doing is just saying that this layer here, let's say layer 5, is younger than, let's say, layer 4. That's all we're going to be doing today, is just looking at what is older and what is younger. And just to point out, the word strata means rock layers. So each of these labeled layers here, these would be an example of strata. So we have 4 principles that we're going to talk about today. And we'll go through each of these individually. We're going to start with the principle of uniformitarianism. It sounds like a lot, but here the word uniform, meaning the same. So what this tells us is that events in the past occurred the same way that they are occurring today. Most of this lesson is actually fairly straightforward. It's just that there's a lot of words we have to know. Some examples of uniformitarianism are weathering and erosion, deposition, volcanism, and plate tectonics. So these things that are happening now on the surface of the Earth happened the same way millions or billions of years ago. Our next rule is the principle of original horizontality. So we have this word horizontal in here, if you think about the horizon or your x-axis. What this tells us is that sedimentary rock layers are always deposited horizontally, like these here. If they are tilted, folded, or broken, that had to happen after. So if we're thinking about the ages of things, the rocks had to deposit first. Anything that happened to make them deformed happened later. Our next rule is the principle of superposition. So position means location. Super means above. So our principle of superposition means when sedimentary rock layers are deposited, the younger layers are always above. This is what we talked about when we looked at our explorations and we decided that the layers on top are younger than the layers on the bottom. So here's an example in real life of the Grand Canyon. We have a photograph here, and then next to it we have the layers in a diagram, A, B, C, D, E, youngest at the top, oldest at the bottom. Our last principle is the principle of cross-cutting relationships. So this is looking at things that might cut through rocks. So if you have an igneous intrusion or a fault cutting through rocks, that intrusion or fault is younger. Now this makes sense if you think about it. I couldn't have cut apart these layers of clay here if the layers of clay hadn't already existed. So this fault had to happen later than the rock actually forming or the clay layers being formed. So here's just another example of a fault here. What I want to talk about now, though, because faulting is relatively straightforward, but I want to make sure we remember what intrusions and extrusions are and how we can tell. So we're looking for something called contact metamorphism. We talked about this when we talked about rocks and minerals. The word contact means to touch. Metamorphism is to change. So we're changing a rock due to its proximity, or touching magma or lava. So if you have magma and lava, remember it's very, very, very hot. Whatever is very close to it is going to change through the process of contact metamorphism. So if you ever see that metamorphism has to be younger than the layer it's in. You can't change a rock if the rock didn't already exist. And it will always be labeled for you on a diagram. So there shouldn't be any questions if you're looking at something, whether it's contact metamorphism or not. And now I just want to review the difference between intrusions and extrusions. So an intrusion occurs. Okay, remember, intrusion is inside. We learned about this when we talked about igneous rocks. When molten rock is squeezing into pre-existing rocks and solidifies. So this never reaches the surface. The way you can tell that it's an intrusion is that there is contact metamorphism along all sides of this intrusion. And this is always going to be younger than anything it's cutting through. Same thing with extrusion. Okay, you have rock on the surface flowing and solidifying. It's younger. Now the way that I can tell this is an extrusion, not an intrusion, is there is no contact metamorphism here. So this top layer made it to the surface as an igneous rock, cooled and solidified, and then layers C, B, and A were deposited above it. So just think about that question. I just talked about it. Think about what you would see for contact metamorphism. Here's an example of an intrusion. You can see it's clearly a different rock type than the rest of them. Now we're still talking about this principle of cross-cutting. So we talked about intrusions and extrusions. Now let's talk about folds and faults. A fold is layers of rock that have been warped or bent by crustal forces. So when we did the activity, we looked at convergent plate boundaries and how they would cause the rocks to fold. So you have folding here. Faulting is a crack along which movement occurs during an earthquake. So that's like when I broke the rocks, or that example where we cut the rock layers and broke them apart. That would be a fault. Now remember that these features are things that always happened later. This can't happen first. It happened later, after the rocks were already formed. Again, you can't fold rocks if the rocks don't already exist. So if we wanted to think about how to label these in order, I have A, B, C, D, and E here. So I like to work from the bottom up, but also you can start from the top. So A is definitely the youngest. It's at the top as far as the layers go. But E cuts through all of them. So E has to be the very youngest. I can see that this part moved up a little bit because this section is smaller than this section. So my oldest layer would be layer C, then B, then A, then D, and then E. I know E is older than D because it cuts it apart, but D has to be older than B, C, and A because it's moving through all of them. So now we want to think about what happens to rocks when they weather and erode. Something called an unconformity is formed. When rocks are eroded, you have a missing section of time. So if you think about it, rocks are deposited, and then over time, if they become eroded, it wears away rocks that were already there. So we call it a missing section of time in the rock record. We don't know exactly how old those rocks are. Something else that can happen with this is called subsidence, which is the sinking of rock or rising water levels. So an unconformity happens when there's weathering and erosion, which means the rocks have been lifted up. Subsidence happens when the rocks sink back underground and more layers are deposited above. So to form this unconformity, I had weathering and erosion, and then the rock layers went back underwater, so sea level probably rose again, and those layers are deposited above. Remember, rocks only form underwater. Sedimentary rocks only form underwater. And here's another example of an unconformity. So again, you have water. You have uplift and erosion. So those rocks went up above the surface where they could be subjected to weathering and erosion. Then the water levels increased, creating this unconformity. So I want to talk a little bit now about how we use relative dating, just very briefly. So we use this to reconstruct the geologic history of a location, or to basically retell the story of a location. The word correlate means to match. So a correlation is to match rocks and geologic events in one area to rocks and geologic events in another. And when we do that, we look at their colors, textures, and composition. So basically, here's an example. If you have a river cutting through something and you have rocks on either side, you can tell if they're the same by looking at those layers and saying, oh yeah, this is the same sandstone here. Oh, it's the same as this one here. They must have formed at the same time. Another way we can use correlation is through something called index fossils. Now, these are very special fossils that are used to determine if rocks were formed during the same time period. What we want to know about index fossils is that they lived for a short period of geologic time, so not a lot of layers. They wouldn't be in a lot of layers, but they existed over a large area. So if you're looking for an index fossil, you want to look for something that's only in one or two layers or strata, but exists across distances. So we'll look at some examples here. So I have my little shells. We want to think about which is going to be the best index fossil. Or I have my little, I don't know what these are, corals maybe, probably not. And then I have these. So we want to think about which one of these is going to be the best index fossil. And so the answer would be these, because they exist across 4 different areas, like if these were 4 different directions, but they're only in one layer compared to like these, where they're in multiple layers. So that's not really giving me a lot of information.